In the previous video, we discussed that smart grids can be adopted in order to increase the penetration of renewable sources in the power system. Moreover, you learned that microgrids can be seen as the building blocks of the smart grid. In fact, microgrids can help to overcome some operational challenges that may arise in the future. In this video, to better understand the functionality and operation of a microgrid, we'll start by having a look at some basic principles about how traditional power systems work. Then, we will go through the main challenges and changes that arise once a large amount of distributed sources is installed. At the end of this video, we will briefly introduce the concept of power electronics interfaces. Traditional power systems consist of three main parts: generation, transmission, and distribution. In traditional power systems, power flows from the generation units to the end-use customers. Electrical energy is generated mainly by large conventional generation units, like thermal power plants, and then sent to medium voltage substations through high voltage transmission lines. Finally, electricity is delivered to the end-use consumers through the distribution network. In order to step the voltage levels up and down, transformers of different sizes are placed between the generators and transmission lines, between the lines of different voltage levels, and between the transmission and distribution areas. Generation, transmission, and distribution are generally vertically integrated in traditional power systems. Power generation is centrally performed at large power plants, which are geographically far from the end-use customers. This makes power systems vulnerable to sudden events, such as adverse weather conditions, accidents, and unexpected component failure, resulting in power system interruptions when the system is not robust enough. Furthermore, in traditional power systems, there is no flexibility on the demand side. This implies that centrally structured power plants are the sole responsible when it comes to matching generation and consumption. This inevitably increases the price of electricity, especially during peak hours. Over the past decade, renewable energy sources like wind and solar have been installed particularly at the distribution side. It is worth mentioning that existing power systems were not designed to integrate highly intermittent renewable energy sources, and therefore existing power systems are facing unprecedented challenges. For example, the introduction of distributed generation at the distribution side has the potential to raise a number of power quality problems, such as voltage variations and harmonic problems. The generation of active power at the downstream network has the potential to dramatically affect the flow of power in the upper network. Unlike traditional power systems, where there is a unidirectional flow of power from generation to distribution, power flows may become bidirectional in future power systems. The upstream power flow can cause protection and stability problems in the existing network because the installed equipment was not designed for such bidirectional flows. Another complex challenge in power systems is generation expansion. The construction of power plants requires large investments, and the optimal size and location of these plants is not easily obtained. The introduction of renewable sources and higher variability of demand due to new technologies like electric vehicles make the generation expansion problem even more challenging. On top of this, expensive transmission and sub-transmission lines need to be built. It should be noted that both generation and transmission challenges are interrelated and must be solved together. Additionally, the distribution network should be reinforced or expanded as well in order to meet the requirements of large loads, such as electric vehicles. At a local level, power quality and voltage should be monitored. At a regional transmission level, parameters related to the stability of the grid, both short and long time scales, should be always maintained at the desired levels. Due to the introduction of renewables, congestion at both distribution and transmission levels can occur. Within a large interconnected wide system, fast and slow reserves must be available to operate in the short term. Finally, for security of supply, adequacy and resiliency of the power grid are to be seriously considered over the long term. Security of supply is defined as a cost-effective risk management strategy that ensures continuity in the provision of energy. This prevents final consumers from being exposed to shortages and blackouts in the coming years or decades. Resiliency refers to the ability of the power systems to prepare for and adapt to changing operational conditions and their capacity to withstand and quickly recover from disturbances and faults. When high participation of distributed generation is desired, proper and fast control and operation should be guaranteed, particularly due to the high uncertainty associated with the renewable energy sources. Additionally, in such extreme conditions, energy storage systems may play a vital role to stabilize the system. They have the potential to store a large amount of electrical energy, which can be provided later during several hours or days, depending on the system design. Power electronics devices are used to control and convert electric power. They serve as an interface to connect distributed sources to the power system. Power electronic devices will also play an important role in keeping the system stable. Thanks to the fast control of active and reactive power that can be achieved, many fast phenomena, such as frequency and voltage deviations, can be effectively addressed. Later in the course, you will learn about their operation and functionalities. So to sum up, in this video we have briefly covered the structure of a traditional power system. Here, the power goes unidirectionally from generation at a high voltage level to consumption at a low voltage level. We discussed some of the challenges introduced by renewable energy sources to the network. Among them, the intermittency and uncertainty in power production and the negative effects in power quality and grid stability. Finally, we briefly covered the generation expansion problem and the effects of power electronics interfaces and battery systems in the network. These new actors will be crucial in order to achieve higher control and to match generation and consumption in future power systems.